My name is Kathleen Hodgkinson and I work for UNAVCO. When I was an undergraduate in the physics department in Belfast, I saw a sign on the notice board that was looking for a graduate student who could study satellite measurements to determine deformation caused by earthquakes. And I just thought that was what I wanted to do. I call myself a geophysicist.
And why?
Because I use lots of different data types now to study crustal deformation processes and help others to study, analyze measurements that have been made by a suite of instruments, not just GPS. In graduate school, as part of my PhD work. When you study GPS and you study crustal deformation, you become interested in the strain in the earth and how the ground around faults deform. And through my work with GPS data, I became interested in the strain measurements that were being recorded along faults, sections of the San Andreas fault. And so I became interested in strain meter measurements then. Okay, a borehole strain meter is, if you were to look at a borehole strain meter, it's about 1.5 meters tall, about 10 centimeters in diameter. And what UNAVCO does is we drill a hole to about 800 feet deep, and then we lower this instrument into the ground, and then it goes all the way to the bottom. We cement it in, and we fill the hole up to the top. You will never see that instrument again. And so what we hope happens is the strain meter becomes coupled to the surrounding rock. And then as the rock deforms, it's deformed by the regional stresses and tectonics, that instrument records the changes. And we can transmit those measurements to the surface and collect them on a data logger and then analyze the signals to try and model the strains that are occurring at depth. UNAVCO has installed 76 borehole strain meters as part of the EarthScope Plate Boundary Observatory program. The first instruments were installed in June 2005, and we installed our most recent one just a few months ago in Yellowstone. The strain meters are they're designed to measure really small, short-term strain transients. So they're installed in regions where we think those kind of signals are occurring. So they're installed along creeping section of the San Andreas fault. We have a lot up in the Pacific Northwest where we know episodic tremor and slip events are occurring. We also have them installed in Mount St. Helens and Yellowstone, and then down around the San Jacinto Fault in Southern California. And so the goal is to capture those really small, short-term strain signals that fall between what you can record with GPS and what you can record with a seismometer. With the volcanoes, what we're interested in capturing is if any small changes in volume in the region or any strain transients that might be induced by changes in seismicity. In the Pacific Northwest, where we have these Cascadia episodic tremor and slip events, the strain meters are providing really high resolution, very good temporal resolution of the strain pulses as they evolve and migrate under that Pacific Northwest Olympic Peninsula. And so researchers are using those data to learn about how slip and tremor are related, and also how the signal propagates. Along the San Andreas, the strainmeters are recording these very nice strain transients that are a few tens of nanostrain that occur over a couple of hours. And they can tell scientists about how the fault is creeping aseismically in Central California. And then as you move down to Southern California around the San Jacinto, what we're hoping is that the strainmeters will be able to tell us more about how stress and strain, stress accumulates around faults that, in that region. Okay, I think what the Plate Boundary Observatory program has done has, first of all, we've really increased our sample rates. So before, in the 1980s, we were getting, you would get one measurement every 10 minutes. And now we measure at 20 samples per second, so really high temporal resolution of those signals. And the data are brought back in near real time in Boulder. And we've also updated our processing techniques, so you can see, just with a few clicks on the web page, you can see the data as it's being recorded just a few hours ago at the strainmeter. We've also installed strainmeters where there were never any strainmeters before. So there were no strainmeters at all in the Pacific Northwest before PBO. And so that's, they've captured really nice signals up there. It's kind of been very rewarding to see the instruments record so well over these past few years. Okay, well, one of the things that PBO has demonstrated is that you can install these instruments well, and you can get very good results very quickly. So within a few months after the installation, you can see these instruments recording the earth tides. You can see little creep events. So we've shown that you can implement large regional strainmeter networks and run them very well. Up until PBO, you would have had maybe 3 or 4 strainmeters installed in a particular area, and then nothing for 5 or 6 years, then maybe 2 or 3 in another area. So to install up to, I think we have 20 up in the Pacific Northwest, record those Cascadia events was pretty unique. And so now what we're seeing is growing interest in countries abroad. So China is currently installing their EarthScope type strainmeter program, where they, I think, are installing maybe twice as many strainmeters as we've done in the EarthScope program. UNAVCO will be installing a network of strainmeters in Turkey on the North Anatolian Fault area this summer, and there's existing networks in the Caribbean, Iceland, and Italy. So there's growing interest in using these type of instruments to study crustal deformation. I've been working at UNAVCO for 10 years, and I still consider myself a bit of a newcomer. It's been 30 years that it's been recording, GPS data, and so every day it seems as though there's a new request from researchers to do something interesting or novel that you'd never heard of before, and so it's just a really fun place to work.